Next, we'll discuss a new concept called the alternating series, and this conversation will be inspired by the following problem. So let's consider a series with the following general term. Now we can easily figure out the first few elements of the sum, and in order for us to analyze the convergence of this series, let's revise what the tools do we have available at the moment. So every time we have to ask ourselves whether a given series converges or diverges, we follow this flow chart. First, we try to recognize whether it is a geometric or telescoping or p-series. In case if we do, then we either find its limit or we determine whether it converges or diverges easily, just by using that criterion that we have for each of this series. And if we don't recognize any of these three, then we continue with the setting up and performing the divergence test. If the limit is not equal to 0, then we are done with the conclusion that the series diverges. However, if the limit is equal to 0, we continue and we perform a convergence test, and we're going to have quite a few of them available here, and we may have to perform a few of them because it's not guaranteed that every test will be conclusive or even applicable for each problem. So this is our game plan for every series. Each of these tests have their own conditions that have to be satisfied before you apply the test, and let's try to apply this strategy to answer whether this particular series converges or diverges. So first we're going to try to identify this as a geometric series. It does not look so. Is it a telescoping series? The answer is also no. Is it p-series? The answer is also no. So it's none of the three. So now we set up the divergence test, and we do that by setting up the limit, hoping that this limit is not equal to 0, and then we'll be done. But this limit is actually equal to 0 because this we can use the squeeze theorem and to show that the limit is equal to 0. So that means the divergence test is inconclusive. All right, so now we want to try to run some of the convergence tests. And there are three available. So we have the integral test, we have the direct comparison, and we have limit comparison tests. But all of these tests require the general term to be non-negative. However, this is where we have an issue. Sign oscillates between -1 and 1, and sometimes it is positive, sometimes it is negative. So because of that, none of these tests can be applied, and that's the problem. So when the elements of the series are not always adding up, and sometimes they're being subtracted because the sign is negative, so we don't have any tools for such case. And being inspired by this problem, we're going to introduce a new concept. And to start, let's consider just a regular series in which every term is positive, And then this series can be written like this. So we just keep adding terms over and over. Now, if we decide to change every other sign from plus to minus, and of course there are two ways of doing it. We can start with the second term, or we can start with the first term. Well, either one of these changes will create what we call alternating series. So in alternating series, every other sign is positive and every other sign is negative. And in general, we can relate this alternating series to the original one by simply throwing what we call the alternating factor in front of the general term. Here we have to be careful with what we put here in the exponent. Since the first term is positive, the power has to be even when n is equal to 1. However, if you write it as -1 to the power n, your first term when n is equal to 1 will be negative, which corresponds to the second series. So this is called the alternating factor. And the easiest way, of course, is to just have it as -1 to some power n or n plus 1, depending on how you want it. However, there are also some non-trivial ways to create alternating factor, such as cosine of pi n. You can easily verify that when n is 1, cosine of pi is -1. So it does exactly the same job as -1 to the power n. And even less trivial, I guess, would be something like this, right? When n is 1, sine of 3 power 2 is -1. So if you see any of these three alternating factors, well, that means you're dealing with an alternating series. All right, and to determine whether the alternating series converges or diverges, we're going to have the alternating series test. Which states that for an alternating series, if the following three conditions are satisfied, that is, without an alternating factor, all the elements of the series or of the terms of the sequence made of the terms of the series are positive, or rather non-negative, and decreasing, and the limit of an as n approaches to infinity is equal to 0. So if all these three conditions are satisfied, then the conclusion is the original series, which is an alternating series, converges. Now, notice how it doesn't tell us that if some of the three conditions are not satisfied, then the original series will diverge. We're not saying that. It's a one-way statement. So if conditions are satisfied, then the series converges. However, if the series converges, it doesn't mean all those conditions are satisfied. And now, if you also take a closer look to these conditions, you may realize that checking whether the limit of the nth term is equal to 0 or not can be combined with the divergence test. So it's like basically, if your limit is not equal to 0, then by the divergence test, that series won't converge. However, if that limit is equal to 0, then in addition to this, you also have to verify the other two conditions, and that will be enough. Remember, in general, that's not enough, but in case of alternating series, that will be enough to conclude that the alternating series converges. So let's try the following example. N goes from 1 to infinity, -1 to the n, 1 over square root of n, and we're going to run the alternating series test. Why? Because we recognize this as an alternating series. And the first condition is that 1 over square root of n must be greater than or equal to 0, which it is. The second condition is that 1 over square root of n must be as a sequence decreasing, and this should be easy to verify if you graph this function on which the series resides, then you'll be able to see that it's decreasing. And so we verified this condition, we verified this condition, and finally the last condition is we have to make sure that this limit is equal to 0, which it is. So we can use the very useful theorem and analyze this limit instead, and this limit clearly is equal to 0. So we can establish the equality both ways, and now we verified all three conditions. So the final conclusion is that this original series converges, and it converges by the alternating series test. Instead of spelling it out, I'm just going to use this abbreviation, AST, the alternating series test. Let's try another example, and let's consider the following alternating series. And we're going to run the alternating series test. Why? Because we recognize this as an alternating series because of the alternating factor. And first, we're going to verify that this is always non-negative, which it is. Then we're going to verify that this is decreasing, and this is when we're going to run into a problem. If you actually graph ln of n, starting at n equals 3, you're going to see that it gets bigger and bigger, or larger and larger and larger, and this is where we fail. So what does this mean? That means that the conclusion, based on what we already have done, even without checking the third condition, is that the alternating series test is not applicable, or we can say is inconclusive, because it only works one way. So if the parameters or if the conditions are not verified, that doesn't mean necessarily anything. However, in this case, if we continue and set up this limit, and remember, this limit is the same limit that we check in the divergence test, and in this case, that the fact that this limit is not equal to 0 implies that this original series diverges, by the divergence test. So the problem will be more interesting or complicated if the limit was going to 0 while the series itself is not decreasing. So that will make a problem more challenging. But this particular problem is this particular series diverges. All right, let's try another example. We have another alternating series. And we're going to run the alternating series test. And we're going to verify all the conditions. Again, why we're running this test? Because we recognize the alternating series. And we're going to verify all the conditions. So it is non-negative. This should be easy to check. It is decreasing. We can check that by plotting it. So as n gets bigger or larger, at 1 we have 1/2, at 2 we have 1/4, so it gets 2 times smaller with every iteration, which means it's decreasing. And 3, we're going to set up the limit as n goes to infinity, and we're going to see that the limit is equal to 0, because 2 to the power infinity is infinity and 1 over infinity is 0. So we were able to verify all 3 conditions of the alternating series test. Therefore, the conclusion is that this series converges, and the reason it converges is the alternating series test. So in this lesson we learn the new idea, that is the alternating series, but remember, our main goal is to answer this question right here, right? We're still curious about this series, which is not alternating. So we don't know the answer to this question yet, but we will learn it in the next lesson.